We're going to take a look in this video a little bit more about the graphs of functions and some of the particular types of characteristics of functions. And we're really going to start by looking at increasing, decreasing, and constant intervals of functions. And then we're going to move on to symmetry of functions. And so you can see in the diagram below that we have the idea of a function increasing. And a function basically means that it's increasing as the y value goes up. So if the next y, so you can see right here on this function, so this function is increasing, 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 increasing until it gets to this point right here, right? So basically, this function is increasing from negative infinity to -2. And then what happens is it starts decreasing. Right? It's going to keep decreasing and decreasing until it gets to this value on the x, which is going to be +2. And so it's decreasing from -2 to +2. And then it starts increasing again up until infinity, as indicated by this arrow. So we're going to conjoin this interval with which it's increasing and say it's increasing from negative infinity to -2, from 2 to infinity as well. And that's what we're aiming for, is we're looking for where the y values are increasing and then the y values are decreasing upon which x span that is occurring. So that's what it means for a function to be increasing and decreasing. And so some of the exercises that we're going to be looking at are those with which we're going to go ahead and have the graph of a function, and we're going to determine where the function is going to be increasing and where the function is going to be decreasing. So let's take a look at a few examples of that. So if we take a look at this first graph that we have this function f of x, and we know that it's going to be decreasing, or at least it's going to be increasing, excuse me, forever. All right, so it keeps getting bigger and bigger and bigger until it gets to this point right here, right, which seems to be -2. All right, similar to the other graph that we just looked at. So it looks like this function is going to be increasing from negative infinity to -2. It never looks like the function is actually going to be decreasing. Okay, so it just keeps going up from the left-hand side. And so what we can say is that this function is not decreasing anywhere. And then where's it staying constant? Well, it's staying constant right here, starting from -2, and then it just keeps going on forever. So from -2 to infinity is where it is constant. Similarly, we have another graph. It's a parabolic sort of function. And the question is, where is it increasing, where is it decreasing, and where is it constant? So this function looks like, okay, while the y value is decreasing, it's decreasing, it's decreasing, it's decreasing. And once again, it just seems like right here at this vertex, which is going to be the point -2, -4, it keeps decreasing until there, and then it's just going to increase anytime after that. So the function is going to be increasing from -2 until infinity. It's going to be decreasing from negative infinity to -2, and it is not constant anywhere. Right? The only place that is really constant is going to be exactly at that point, -2 for x, but it's really neither increasing nor decreasing there. So it's just a point of inflection. Another sort of thing that we can look at with respect to graphs is the idea of symmetry. Symmetry basically means that it looks the same on both sides when you cut the graph in half. So for instance, if we have a graph similar to the first one that we have here, this is a graph which is symmetric about the y-axis, because if we cut it right in half with the y-axis, there's a point here and a point here at which the values are precisely the same. So in other words, if f at x is equal to f at -x, that means that the function is symmetric about the y-axis. And it also means that it's going to be an even function. Now, if we took a point on the function right here at f at 2, and if you just took the opposite of that for every point on the graph, it was equal, then that means that the function is going to be symmetric about the line y equals x. So, and the line y equals x is just basically this line right here that passes right through the origin. And that means that it's an odd function. Or more specifically, if f at minus x is equal to the opposite of f at x. All right, that's the definition of an odd function. And then if there's no symmetry, that just means it doesn't fit this criteria, nor does it fit this criteria. So what we're going to do is we're going to take a look at both the algebraic expressions as well as graphs, and we're going to determine whether a function is even, odd, or neither even nor odd. And one of the ways to do that is start by plugging in f at minus x. All right, so we're just going to substitute negative x back in, and then what we're going to do is we're going to evaluate this at each of the different expressions. So we have this function f at x, and what I'm going to do is I'm going to substitute negative x back in for each of the x's. So we get negative x quantity square plus the absolute value of negative x plus 3. And one of the things that we probably remember is that anytime we square a negative number, as long as it's a real number, it goes positive, right? And another way to write this algebraically, if you really wanted to break it down, is we could rewrite this as -1 squared times x squared if we wanted to factor out the -1. But remember, whenever we square -1, that just becomes 1. So this first term just becomes x squared. If you take the absolute value of negative x, that just becomes the absolute value of x. All right, the negative just goes away. So we can just say this is really the absolute value of x, and then 3 is just 3. All right, so notice that this, when we simplify it, is the exact same thing as the original function. And since it is the same as the original function, so we can say since f at minus x equals f at x, the original function, we can say that this is an even function. Right? And that's what we're looking for. We're looking to determine whether it's even, odd, or neither even nor odd. Another example is if we substitute negative x back into this function g, and this is going to be negative x cubed plus negative x. And again, similar to what we looked at before, another way to write this is -1 to the third times x to the third plus a negative x. And we know that if we raise a -1 to the third power, negative times negative times negative, that's going to stay a -1. We bring down the x cubed, and then this plus a negative x just becomes a negative x. And we notice that this is actually going to be the opposite of what we started with. And so since it is the opposite, what that means is that f at minus x is equal to the opposite of f of x, okay? Which implies that we have an odd function. All right, and again, odd means that it's symmetric about the line y equals x. Right. And remember, even function means that it's symmetric about the y-axis, right? And then finally, we have this expression or this function, x squared plus x plus 3. We're going to substitute for negative x. So that's going to be opposite of x squared plus opposite of x plus 3. And again, we know that when we square a negative, that just becomes x squared. We can see that from the first example. This becomes a minus x, and then 3 is just 3. All right. And if we look back, well, the first sign stayed the same, and the last sign stayed the same. But if you look at that negative x, it became, or the positive x that it initially we had in the function, it just turned into a negative x. And so what this means is that it's neither even nor odd. It has to either all change or all change signs, or none of the signs have to change. Okay, so we could say since f at minus x does not equal f at x, and since f at minus x does not equal the opposite of f of x, that means that this is neither even nor odd. All right, and we can say g is neither even nor odd. All right, so, and that certainly happens. One last example we can take a look at is with respect to the graph of a function. And let's take a look at the points with which we're given. So right here we have -3, and it gives us the exact same value as +3. All right, so f at -3 is equal to 1, and f at +3 is also equal to 1. Similarly, if we take a look at these other two values, we know that f at -1 is 0, and we also know that f at +1 is 0. And what it looks like, and even if I were to pick this point right here, we could even say that f at 2 is going to be equal to a half, and f at -2 is also equal to a half. And what this looks like is that f at -x is going to be equal to f at x. All right, so notice that anytime we throw in the opposite values, we still get the exact same numbers for the output. And that's the very definition of what it means to be an even function. So we can say, hence, f is an even function. All right. So hopefully this helps you to see how to determine if a function is increasing and decreasing on which intervals, and then also to determine if a function is going to be even, odd, or neither even nor odd. In the last video with the functions, we're going to take a look at one last trait of functions, or one last operation, and that's going to be called the difference quotient of that function.